this video, we're going to look at Le Chatelier's principle. This particular principle is heavily involved in our work with dynamic equilibrium. It enables us to predict in which direction the reversible reaction will move when we change the conditions in the experiment. In essence, it can be summarized with a simple phrase that the equilibrium position moves to minimize the effect of a change in conditions. That's Le Chatelier's principles if ever you're required to quote it. There are three main ways that we can change the conditions in experiment. We can change the temperature. We can change the pressure if we're dealing with gases, or with liquids, we can change the concentration. So if we look at each of these in turn, in any reaction that we have, A plus B as an example, going to AB, one direction of this reaction will be exothermic, and in this case, let's say it's the forward reaction, and the other reaction, therefore, will be an endothermic reaction. So we have heat being produced in this direction, and we have heat being taken in other words, a cooling effect in this direction. So in the case of this, if we decide to increase the temperature of the reaction, we will be making this hotter. So the reactants will get hotter. Now, to minimize the effect of that, what the reactants will do will try to cool down the reaction. In other words, to do the opposite of making it hotter, we'll promote the reaction that cools it down. So if we increase the temperature in this case, we will promote the exothermic reaction, which means the dynamic equilibrium will shift to the A plus B side of this equation. Now, for us as chemists, in this case, that would not be very useful, because if we're doing this reaction at all, we probably want to promote the actual product that we're making. So if we wanted to do this, we would reduce the temperature, in other words, to cool it down, and if we cool down the reaction will try to do the opposite of that. It will try to increase the temperature, which means it will promote the exothermic reaction, which is the forward reaction. So as a result, if we cool down the experiment will react to try and increase the exothermic reaction and therefore produce more of our products, A plus B. If we start to consider instead the number 2 situation of pressure, we have, in the case of, and the best example to use here is the Haber process, we have a situation where we have some nitrogen, N2, plus some hydrogen, H2, and it's going to make, in fact, remember it's a reversible reaction, and it's going to make ammonia, which is the 2NH3. So, when we look at this, if we look at the reaction of these gases, at this side of the equation we have 1 molecule of nitrogen, but we have 3 molecules of hydrogen, making 4 molecules on this side. These 4 molecules exert a pressure on the containers. On the opposite side of the reaction, we just have 2 ammonia molecules, and those 2 ammonia molecules are the ones exerting the pressure on this side. Now, if we change the conditions of the pressure of this reaction by increasing the pressure, we will try and put more pressure on the container. So if we wanted to decrease the pressure, the easiest way to do that is to reduce the number of particles or molecules that are pushing against the side of the container. So if we wanted to decrease the number of molecules, the easiest way to do that is to move the reaction towards the ammonia side, because when we move towards the ammonia side, there are less molecules present. We've gone from 4 to 2 for each of these that react. So by increasing the pressure, we encourage the reaction in the direction that will decrease pressure, and that is the one to the side with the least molecules. So increasing the pressure will promote the reaction that reduces the number of molecules. So in the Haber process reaction, you'll know that the conditions of the reaction are carried out at 200 atmospheres. This is 200 times atmospheric pressure, so this is incredibly high pressure. It could be higher, but the economics of this means that if you tried to increase it higher, you would not get your money's worth from the reaction. So simply 200 atmosphere is what it's limited to. Our third situation is of concentration. So again, if we considered the Haber process as a reaction of concentration, we have our nitrogen plus our hydrogen forming our ammonia. Right? So as this reacts, we maybe have only 5% of our product as ammonia and 95% of our chemicals as the reactants, nitrogen and hydrogen. Now, if I can reduce the concentration of ammonia by removing it, this will reduce the concentration of ammonia on this side. If we reduce the concentration of ammonia on this side, then Le Chatelier's principles will say that the reaction will compensate this by moving more of the nitrogen and ammonia over to this side of the equation. In other words, by removing this, we'll reduce that concentration. So to increase the concentration, more ammonia or more nitrogen and hydrogen will move to this side. So we'll promote the forward reaction. So in the case of Le Chatelier's principle, by removing our product, we increase the forward reaction. So remove the product increases the forward reaction. That is in principle how the three different changes of conditions react with Le Chatelier's principle. So, for one, in summary, Le Chatelier's principles explains how the dynamic or the equilibrium position in a dynamic equilibrium can be changed by changing the conditions. And Le Chatelier's principle says that it will change to minimize the effect of any change that we make. In the case of temperature, if we increase the temperature of the reaction, Le Chatelier's principle says that we will then promote the endothermic reaction. If we decrease the temperature, we'll promote the exothermic reaction. In the case of pressure, if we increase the pressure, we will promote the reaction that serves to reduce the number of molecules. In the case of the Haber process, this is the forward reaction. If we reduce the pressure, we will rather promote the reaction that reduces or increases the number of molecules. And in the case of concentration, if we remove some of the concentration of, say, the product, then the reaction of the forward direction will be promoted to produce more of that reaction. If, for instance, we added more ammonia into this, we would promote the reverse reaction. That's a summary of Le Chatelier's principle.